you're going to say, I'm not building this structure out of rubber band. I'm not building it out of rubber. I'm not building it out of some soft tissue type material. I'm building it out of something that's really stiff. Okay, so relatively as metals go. So maybe I'm going to build it out of steel, I'm going to build it out of wood, I'm going to build it out of aluminum or something like that. I'm not going to build it out of rubber. Okay, so that's already an assumption. So notice that already we have said something about stiffness. So remember, when you're doing force calculations, the stiffness business automatically comes in. Okay, so we are talking about stiff structures here. So this will make our life very easy. So our free body diagram, this is a joint B, and then I have 2000 newtons external force, FBC, FAB, and this angle is theta. Okay, so it's easy for us to do the calculations. So now I'm going to do summation of all the forces in the x direction. Summation of all the forces in the x direction. This way positive equal to 0 will give me minus FAB minus FBC cos theta equal to 0. Summation of all the forces in the y direction equal to 0 will give me FBC sin theta minus 2000 equal to 0. So this immediately allows me to calculate the forces. FBC equal to 2000 over sin theta, FAB equals minus FBC cos theta. So I want you to observe two things. First thing is FAB is less than 0, it's compression. Whenever you see a long bar under compression, that's the bar to study for stability. Okay, so this means this is an issue. So I'm telling you general rule. So compressive bar should be studied for stability. Okay, in fact, if you look at our crane, that's why the base bar, that is this bar, that's why this bar is so big, because it's under compression. It's a long bar under compression, and long bars under compression have to be very stable, and stability requires the bar cross section to be large. Long bars under tension don't have stability issues. That's why this is in tension. So it's okay. Compression means danger. Okay, so if you have compressive bars, then you have to worry about stability, that is buckling and all of that. If it is tensile bars, you are okay. So you see why we did that. So now we are beginning to see how this whole thing works, right? So now we cannot proceed without some angle. So what I'm going to do is I'm going to enter this angle. So this is where our Excel comes in very, very handy. So I'm going to say, okay, angle, let's say, what shall we put? 30 degrees. Okay, 30 degrees is a very shallow one. So we are going to put 50 degrees, 60 degrees, whatever you like. 60 degrees. If you put angle equal to 60 degrees, then FBC will be equal to, let us see. So let us put it up here. Load equals 2000 newtons degrees. FBC will be equal to load divided by sine of 60 times pi divided by 180. So please remember, that Excel always uses everything in radians. So I'm going to say that it's 2309 newtons, and then sorry, let us make sure. So it's, yeah, that's right. And then FAB equals minus of FBC times cosine of theta star phi over 180 newtons. So I want you to notice a couple of things. First, we guessed the angle. So we'll get back to the thinking tools. So we guessed the angle. Found FAB and FBC. Notice that FBC is always greater than 2000 because of the sine theta term, and in fact greater theta, so theta increases, FBC will decrease. Okay, so that's a good thing, because you could make the angle very stiff, I mean very shallow, or very not very shallow. For example, what if I put 80 degrees as my angle? Notice that FBC is almost 0, FAB is almost 0, so this is good. So the larger the angle, the better it is. In fact, it is because they want a large angle that they have all this elaborate stuff. They are trying to make this angle as large as possible. So they want to make this angle large, that angle. Okay, so they work really hard to make, so that's why they have all this elaborate stuff. And you cannot make it too large, because then this will become very long. Okay, so that's how a crane works. In our case, let us say I don't want to make 80 degrees. 80 degrees is a huge angle. So let us keep it at a lower 60 degrees. Okay, so now I got FBC and FAB. One interesting thing that I want you to see is that in this particular case, I could find forces, internal forces, without looking at deflections. Such a system is called statically determinate. I'm sure you've heard this name. Statically determinate means I can find the internal forces without looking at the deflection of the system. This works only for almost rigid bodies. A rubber band can never be statically determinate, or almost never be statically determinate. Let me be very careful. There may be some peculiar situations in which it can be, but a typical rubber band structure will never be statically determinate, because it's not stiff enough. It's not almost rigid. So only almost rigid structures are statically determinate. Because of that, I can do strength analysis. Why do we care so much about statically determinate? Because I can do strength analysis right here. So for a statically determinate system, I can do a strength analysis immediately after writing the equations of equilibrium and solving it, because I can solve for the forces. For a statically indeterminate system, I cannot do it. I have to actually look at stiffness and so on. Okay, so for statically determinate, statically indeterminate,